Solving quadratic equations by graphing, Part 1. In this lesson, our friend Joe Quadratic will be solving quadratic equations by graphing. With this method, he will be able to solve quadratic equations such as this one, n squared minus 2n minus 3 equals 0. In order to graph this equation, something will have to be different. With only one unknown, there is no way for him to graph this equation on a coordinate plane. To explain solving by graphing, the technique is to change a quadratic equation into a quadratic function. And wherever that graphed function touches or crosses the x-axis will be found the solutions to the quadratic equation. It's as simple as reading the solutions as points on a number line. And here we see a number line along the x-axis, and that's what the x-axis really is, just a number line, one dimension of a two-dimensional coordinate plane. For instance, this function f of x graphed here in blue crosses the x-axis at 2 points. And based on this graphed version of quadratic function, the solutions would be x equals negative 3 and x equals 5. It's as easy as reading solutions off a number line. There is a four-step process that, when applied, will enable us to solve this or any quadratic equation using this technique. And here's a secret you might want to keep in mind from this lesson. This technique of solving by graphing applies to all types of one-variable equations, where you are just solving for real numbers, not just quadratic equations. Step 1. Solve one side of the equation for 0. Step 2. Change the 0 to y or f of x to create a function from the equation. Step 3. Graph the function. And Step 4. Look for where the graphed function touches or crosses the x-axis. Those will be the solutions. Now back to our problem. Since the function is already equal to 0, Step 1 has been completed for us. Now we apply Step 2. We change the 0 to y. To solve the quadratic equations by graphing requires skill in the process. I've created a video lesson more specifically targeted to this skill of graphing quadratic functions. The title of the lesson is Graphing Quadratic Functions Made Easy, and you may click on the box on the left to be directed to that video lesson at this time. Now we are at Step 3, graph the function. To get the function in x and y variables, we change the n variable to x. Now we have created a quadratic function from a quadratic equation that we can graph on a coordinate plane. For cosmetic purposes, Joe switches the function to have the dependent variable y on the left side, where he is more accustomed to working. We create a table where we will obtain points to be graphed. The question now is, where should we start? Fortunately, there's something called the quadratic formula that can help. But it's just this part of the formula, x equals negative b over 2a, that is the key to where we're going to start. So this is our axis of symmetry formula, x equals negative b over 2a, and that's what we're going to use to find the center reflective line, or axis of symmetry, for our graphed quadratic function. But to use this formula, we need to identify the a and b of this quadratic function. First, this function has to be 1 in the standard or general form of a quadratic equation, y equals ax squared plus bx plus c. And we see that it is in this form of a function. And accordingly, a equals 1, b equals negative 2, and c equals negative 3. Now we rewrite the axis of symmetry formula with parentheses into which the a and b can be inserted. The b goes in the numerator, and the a in the denominator where the parentheses are. And here, negative 2 replaces b in the numerator, and 1 replaces a in the denominator. And all simplified, the axis of symmetry is x equals 1. So this value for axis of symmetry, x equals 1, goes as our first input value for our table in the center cell in the left column of the table. And from here, Joe takes the input value of 1 and inserts it into the original function where the x's are in 2 places here. So we end up getting f of 1 equals 1 squared minus 2 times 1 minus 3. And this simplifies to f of 1 equals negative 4. And we place this output value of negative 4 right next to the 1 in the right column of the table. Now with that central value determined, we can fill in the next 3 values greater than 1 and the next 3 values less than 1. For a next point, we have as our function a y-intercept of negative 3, which we can write as f of 0 equals negative 3, which we place in our column of output values. And because of symmetry, the input value on the other side of 1 will also have to have an output of negative 3. Next, we'll try an input value of 3, and working it all out, we have 9 minus 9 equals 0. And so 0 goes next to the 3 in the table on the right side. And because of symmetry, the output value for an input value of -1 is also 0. And finally, we input 4 to get the table filled in, and that would be f of 4 equals 16 minus 8 minus 3 equals 5, which takes its place in the table next to the input value of 4. And because of symmetry, f of -2 is also equal to 5. He now gets his graph paper set up to plot the points. He sets up his axis of symmetry at x equals 1, and next we'll plot the starting point or vertex at 1, -4. And here are all the other points plotted. And here's the parabola drawn through the points. After graphing, we look to step 4. We can look along the x-axis and pinpoint the solutions to this equation, which are x equals -1 and x equals +3. These points along the x-axis can be called roots, solutions, x-intercepts, and zeros. Going back to the original unknown n, he says that the solutions for this original equation are -1, n equals -1, and 3, now boxed in as our correct answer. Here's the next equation we'll look at, -x squared plus 3x equals -4. Stop the video, see if you can solve this one by yourself. Hint, you'll need to set the right side of the equation equal to 0, then replace that 0 on the right side with the dependent variable y. Restart the video after you've graphed it. Step 1, we get the right side equal to 0 by moving the -4 to the left side of the equal sign. This becomes negative x squared plus 3x plus 4 equals 0. Step 2, we change the equation into a function by changing the 0 to a y and swapping sides, so the y is on the left side of the equal sign. And step 3, graph the function. We draw a table that we'll use to get the points to draw our graph. Next, we get out our axis symmetry formula, x equals -b over 2a. Since this equation is now in standard form, we have a equals -1, b equals 3, and c equals 4. Here's the form where parentheses are placed into which the values of a and b can be inserted, and here's the form with the values of a and b inserted in the formula, which simplifies to 3 over 2, which is 3 halves and may even be written in the decimal form 1.5, which we can now place in the table as our central input value. And to find the vertex, we find f of 3 halves by inserting 3 halves wherever there is an x. And working it out, we have f of 3 halves equals -9/4 plus 9 halves plus 4. And converting each term to a common denominator of 4, we get f of 3 halves equals -9/4 plus 18/4 plus 16/4, which simplifies to 25/4 or decimalized 6.25, which we place next to the 3 halves in the table on the right side. And in the table below, 3 halves, we place 2, 3, 4, and 5, and above 3 halves we place 1, 0, -1, and -2. And all the output values are placed in the table to the right of the input values in the right column. And here's the coordinate grid on which we'll plot our points and draw our quadratic function. Here's our axis of symmetry at x equals 1.5, and here's the vertex plotted at 3 halves, 6.25. And here are all the other 8 points plotted, and here's the curve drawn through all the points. And now step 4. And for our solutions, we look along the x-axis, and from the x-axis we see that the solutions are x equals -1 and x equals 4, which is corroborated by the data in the table because these input values of -1 and 4 for x are where the y values equal 0. So we box in these answers as correct. And these are the solutions to the original equation, -x squared plus 3x equals -4. You might remember from the video where Joe Quadratic was introduced to the quadratic equation he tried to solve but could not using the method of solving linear equations. He tried to combine 3n squared and 5n but could not do it because they are unlike terms. Now Joe will try to solve this quadratic equation by graphing. Joe changes the 0 to y and the n to x, convert it to a function he can graph on a coordinate plane. Now we switch it around to get the dependent variable on the left side. Now to step 3, graphing the function. And now we get the blank version of the formula into which we can insert the a and b from the quadratic function. We start by getting the axis symmetry formula and identifying a, b, and c from the quadratic function in standard form. A equals 3, b equals 5, and c equals -2. We end up with an axis symmetry of x equals -5/6. Now we use the input of -5/6 to find the y value of the vertex. We have f of -5/6 equals 3 times -5/6 squared plus 5 times 5/6 minus 2. So this becomes f of -5/6 is equal to 3 times 25/36 minus 25/6 minus 12/6, which equals 75/36 minus 37/6. And using a common denominator of 12, we have f of -5/6 equals 25/12 minus 74/12, which equals -49/12, or approximately -4.083. And we place these values in the center of our table. Next, we fill in the integer values greater than -5/6 and less than -5/6. Next, we enter the output values for these inputs. These other outputs are a lot easier than finding the vertex because their inputs are not fractions like the x value of the vertex of -5/6. Here's the coordinate plane we'll be using to plot the points and graph the function. Here's the axis symmetry at x equals -5/6. Here's the vertex plotted at -5/6, -49/12. And here are all the other points plotted except for 2, 20, which is too high to appear on our grid. And here's the graph of the function drawn through the points. Now we get to step 4, find the solutions along the x-axis. Here's one solution, or x-intercept, at x equals -2. And this makes sense because we can see this is a solution as a 0 in the table. But what about this other 0? We see that it exists because we see it on the x-axis between x equals 0 and x equals 1. We'll call it a question mark until we find exactly what it is. In the table we don't see that second 0 for y, but notice that y is -2 at x equals 0 and 6 at x equals 1. One thing we can do is try different numbers until we get closer to a solution. Here we try 1/2 or 0.5 as an input value. The output value simplifies to y equals 1.25, pretty close to y equals 0, but still not 0 and therefore not a solution. Next we can try 0.25. We get an output value of -0.5625, closer to 0, but 0.25 or 1/4 is still not a solution. Next we're going to try 0.35 for x between 0.25 and 0.5. We get y equals 0.1175, even closer, in fact very close, but still not 0. Joe realizes that to get that second answer, it might be possible by continuing his search, but Joe has some important things to do. This is starting to take away from his basketball time. To find solutions by graphing where we're not on an integer, such as this problem, a graphing calculator can be very useful. And you can find a video on how to use a graphing calculator to do this type of problem by clicking on the box here. By the way, the value of the second solution is 1/3. How do we know that the 1/3 is the solution? Since the difference between the axis symmetry and -2 on the x-intercept on the left side is 7/6, if we add 7/6 to -5/6, we will get 1/3. And here are the 5 different methods of solving quadratic equations that we'll be covering in my series. We have the square root method, solving by factoring, solving by graphing, using quadratic formula and completing the square. You may click on any of these to go to that particular lesson. In addition, there is a solving quadratic equations flowchart that filters you through the different techniques of solving these types of equations. This has been Solving Quadratic Equations by Graphing, Part 1. Thanks for viewing.